There is a number that sits at the foundation of everything you have ever seen, touched, or experienced. It is the smallest distance that physics says can have any meaning. Below this distance, the concept of space itself stops making sense. In the same way that asking what is north of the North Pole stops making sense, that number is 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000016 meters. It is called the Planck length, and here is why it matters to this conversation. If you took a spacetime pixel at the Planck length and enlarged it to the size of a grain of sand, atoms would be the size of entire galaxies. The universe, at its most fundamental level, appears to have a resolution limit, a minimum unit below which reality stops being divisible. And to a physicist who also thinks about computation, that looks less like a property of nature and more like a property of a digital system. A system designed with finite processing power that cannot afford to simulate the universe at infinite precision, so it builds in a minimum pixel size below which the render simply does not go. This is not fringe thinking. It is something that serious physicists, cosmologists, and computer scientists at institutions including Caltech and MIT have written about and published papers. And when you put it alongside everything else that the physics of this universe seems to suggest about its own architecture, the question of whether the reality you are experiencing right now is genuine stops being a philosophical novelty and starts being something that deserves a more careful answer than most people have given it. The modern form of this argument was constructed by philosopher Bostrom at Oxford University in a 2003 paper that has since become one of the most discussed philosophical documents of the 21st century. Bostrom did not claim to prove that we live in a simulation. He presented something more unsettling, a logical structure he called the trilemma, which forces anyone who thinks carefully about it to conclude that at least one of three propositions must be true. The first proposition is that the fraction of civilizations like ours that survive long enough to develop the computational power to run detailed simulations of conscious minds is very close to zero. In other words, almost every civilization destroys itself before reaching that point. The second proposition is that civilizations which do reach that computational capability almost universally choose not to run such simulations, for reasons of ethics, resource conservation, or complete loss of interest. The third proposition is that we are almost certainly living in a computer simulation right now. The logical structure behind this is not subtle. If civilizations do survive to posthuman stages and do choose to run simulations, they will run enormous numbers of them. A single posthuman civilization could run billions or trillions of simulations, each containing billions of simulated conscious minds. The biological minds of any civilization are a finite set, comparatively tiny. By simple mathematics, any given conscious experience is astronomically more likely to be one of the vast multitude of simulated experiences than one of the small number of biological ones. The only ways out of the third conclusion are the first two. Either we will not survive long enough to build the technology, or we will build it and choose not to use it. Bostrom himself said he did not know which proposition was true, but he was clear that one of them had to be. Now here's where this stops being purely philosophical and starts touching physics. Because if the universe we experience is a simulation, it should have certain properties that a real, infinite, continuous universe would not have. Properties that look suspiciously like the properties that any system with finite computing resources would generate. And when physicists look at the actual architecture of the universe, they find a remarkable number of things that fit that description. Start with the speed of light. The speed at which information travels through the universe is not, as most people intuitively imagine, simply very fast. It is an absolute upper limit. Nothing can transmit information faster than light, regardless of the energy, the technology, or the method used. In information theory and computer science, this kind of hard limit on information propagation has a specific meaning. It is what you would expect from a computational system with a finite clock speed, a maximum rate at which the system can update its state. If you were designing a simulation and needed to enforce a processing rate constraint across all operations simultaneously, building in an unbreakable maximum information speed would be exactly how you would do it. The speed of light behaves, in the language of computer scientists, like a hardware artifact, a constraint imposed not by any physical law in the usual sense, but by the architecture of the system running the simulation. The Planck length reinforces this. In quantum mechanics and in the theoretical frameworks of loop quantum gravity, physicists have found evidence that spacetime is not a smooth, continuous fabric, but is composed of discrete units. The smallest of these units is the Planck length. Below that scale, quantum fluctuations make the concept of location meaningless. You cannot ask where something is at a precision below the Planck length and get a sensible answer. If you were building a universe from scratch on a computational substrate and needed to limit memory and processing requirements, you would build in a minimum resolution below which you would not bother to render anything. The Planck length behaves exactly like the pixel size of a simulation running on hardware with finite memory. To be precise about the scale, if a Planck length pixel were enlarged to the size of a grain of sand, atoms would be the size of galaxies. We are talking about a resolution so fine that our most advanced instruments cannot come close to probing it. But it exists, and it has a hard limit. Then there is quantum mechanics itself, and specifically the feature of the quantum world that disturbed physicists most deeply when they first encountered it, and that has never been fully explained in the centuries since. The measurement problem. In quantum mechanics, a particle does not have a definite position or a definite momentum until it is measured. Before measurement, it exists in what physicists call a superposition, a spread of possible states, each with a probability. The act of measurement causes what is called the collapse of the wave function. The particle, suddenly, from a practical standpoint, acquires a definite state. This is not a description of our ignorance. It is not that the particle had a position all along and we just did not know it. Experiments, including the famous delayed choice, quantum eraser experiments, have ruled out that interpretation with high confidence. The particle genuinely does not have a definite state until something interacts with it. Now consider this from a computational perspective. A video game does not render the parts of the world the player is not looking at. It would be computationally wasteful to maintain the full detail of every object in a scene that no camera is pointed at. Modern game engines are built around exactly this principle. Only the portions of the world that are currently being observed are rendered at full resolution. Everything outside the frame of observation is handled with simplified approximations. And quantum mechanics says the universe operates by almost the same logic. States are not fully resolved until they are observed. The universe, at its most fundamental level, seems to compute only what is being looked at. The third pillar of physics that keeps appearing in this conversation is what physicists call fine-tuning. The fundamental constants of nature, the gravitational constant, the mass of the electron, the strength of the electromagnetic force, the cosmological constant governing the expansion of the universe, are calibrated to specific values with extraordinary precision. If any of these constants were different by a tiny amount, the universe would not contain stars, planets, chemistry, or life. The cosmological constant, for example, is fine-tuned to approximately 1 part in 10 to the power of 120. That is a number with 120 zeros. Cosmologists call this the most extreme fine-tuning problem in all of physics. The natural explanation for fine-tuned parameters, the explanation that requires the fewest additional assumptions, is that someone set them. An engineer designing a simulation and wanting it to produce a rich, complex, interesting universe would need to choose parameters carefully. Parameters that produce only hydrogen gas, spreading uniformly through empty space, are boring and computationally uninteresting. Parameters tuned to produce galaxies, stars, planets, chemistry, and consciousness are the parameters you would choose if the simulation was meant to generate something worth running. The counterargument is real and must be taken seriously. In 2025, Italian astrophysicist Franco Vazza published a paper in Frontiers in Physics titled exactly what it sounds like, an analysis of whether there is enough energy in the observable universe to simulate the universe to the precision that physics actually requires. His conclusion was that there is not even close. Simulating the full observable universe down to the Planck scale would require computational resources that exceed anything available within the observable universe by many orders of magnitude. This is a fundamental objection that the simulation hypothesis has to answer. In 2026, researchers at Edge Institute published a direct response to Vazza, arguing that his objection applies only if the simulator's universe is governed by physics similar to our own, specifically, by the same constraints on energy and computation that apply here. If the simulator operates in a different physical substrate, with different rules governing what energy can accomplish, the energy constraint that Vazza identified does not apply, which does not resolve the question. It merely pushes it up one level. The simulator's universe, whatever it is, must also have physical rules, and those rules might or might not make the simulation feasible. We have no way of knowing. What makes the alien framing of this specific question both more specific and more interesting than the general simulation hypothesis is the time component. If the universe is a simulation, the most likely operator is not a deity in any traditional religious sense, but exactly what the Bostrom argument suggests. A civilization that evolved within the universe, reached technological capabilities sufficient to run simulations of conscious minds, and chose to run them. If that civilization is alien, meaning extraterrestrial in the sense that it evolved elsewhere in the universe rather than on Earth, then the simulation hypothesis and the question of alien life are the same question. Finding the simulators and finding the aliens are identical searches. A civilization billions of years more advanced than ours, having survived the technological bottlenecks that most civilizations apparently do not, might find running simulations of earlier eras of cosmic development to be the most interesting thing available to do. Ancestor simulation. The specific case that Bostrom identified as the most likely use of posthuman computational power, a simulation of a universe containing beings like us, at our stage of development, looking up at the sky and wondering whether anyone else is out there. The deepest implication of this, and the one that is hardest to sit with, is what it means for the search for extraterrestrial intelligence if the simulation hypothesis is correct. If we are in a simulation, then the beings running it are, by definition, the most advanced civilization we could ever encounter. They are not somewhere in the galaxy waiting to be found by a radio telescope or a space probe. They are, in a sense, everywhere, because they are the substrate on which everything we experience exists. Contact with them would not look like a signal from a distant star. It would look like what every religious tradition has described as contact with the transcendent, a glitch in the rules, an event that physics cannot explain, a moment in which the normal behavior of reality is suspended in a way that seems impossible and that leaves no trace that conventional science can follow. Whether such moments have occurred, are occurring, or will occur is a question that this framework cannot answer from the inside, and that is perhaps the strangest property of the simulation hypothesis. If it is true, it is a fact about our universe that our universe, from within, cannot prove.